Thank you very much. So yeah, thanks a lot for the invitation to be here. It's great. It's a great place. I didn't know it before, but it's really a very nice environment. And yeah, a disclaimer, I'm not talking about random tensors today. I'm talking about tensor networks and the way we use them for quantum many-body systems. And I hope you see some connections also to the topic in the first talk. So yeah, as Matthias said, please interrupt me any minute and ask questions all the time. It will be much better to that you follow some of what I say than just letting me run till the end. Okay, so what I want to talk to you about is what are these tensor network states, how we see them in quantum many-body systems, and how we use them numerically. So this is the topic in which I work, these numerical algorithms to use tensor networks for solving quantum many-body problems. And today, in particular, I would like to define what these tensor networks are, and at least from this perspective that I'm mentioning, and what are the main families that we talk about. These are matrix product states, matrix product operators, PEPs, and well, some others. And there will be some other talks that use these tensor networks, like Norbert this afternoon will talk about PEPs. So at least you will have seen the connections. And yeah, by the way, so some of you is keeping track of the chat, right? To let me know if somebody is asking, because I'm not keeping an eye on that. Okay, so what are tensor networks? Yeah, in the context, I mean, of quantum many-body systems, because of course tensor networks have appeared in many other contexts in say, science, and in particular in applied mathematics. Well, in the context of quantum many-body systems, what we want to do is to understand the state of a system which is composed of say capital N, capital N small quantum systems. Each of them has a finite physical dimension, which is what we label as small d. Can you see this? And we have a system of these quantum systems that interact with each other according to some model that explains some physical problem that we want to solve. So what we want to do is to describe equilibrium states of that thing. That could be thermal equilibrium states, ground states, so something that describes the properties of matter that we see. But of course, we want to go also beyond that, and let's say we want to describe interesting physical states, so the states that physical systems sort of explore. And before going into what tensor networks are, I need to introduce, or I would like to introduce, the pictorial representation, the language of diagrams that we use to talk about this. And this turns to be very useful to present algorithms and to present properties of this object. So a tensor, for us, is, well, basically the same thing. It's a multidimensional array. So pictorially, we represent it with some kind of figure. I'll use most of the time boxes, but sometimes I don't think this is working very well. So I'll just not point at anything. So sometimes we use circles, but I think I will try to be consistent, and most of the time I will be using boxes. And each of the legs is an open index, meaning one of the dimensions of the tensor. So for instance, in here you have an 8-rank tensor, arbitrary one. I'm not specifying what are the dimensions. And like this object with all the legs means all the components of the tensor, so the whole object. So when I sometimes write the indices of the legs, that's typically to make it particular for one particular component of the tensor. But if I don't write the indices, then it means just the tensor, the whole object. In this language, in these pictures, putting the legs up or down or in some direction doesn't have a particular meaning. So this is typically understood from the context of what we are saying. So sometimes we use like always the same direction, like pointing up or pointing down always, to talk about vectors, like in the language of the first talk. So we could point all the legs in the same direction and keep it consistent. So in some context, people define a more concrete meaning for the different legs, like where they are pointing, and this can be done consistent. But what I'm talking about now is what everybody uses, what is general use in the literature about tensor networks. So I'm not assigning any direction to the leg, but it can be done. Anyway, so the simplest example of a tensor is a vector. A vector is just one of these objects with just one leg. And if I write the component as in here, if I write the index, this means that this is one component of the vector, like this v sub i, and this I runs up to some dimension that I'm calling capital D in here. One step beyond is a matrix. A matrix has two indices. Typically, to talk about matrices, I will write each leg pointing in an opposite direction. But there is basically no difference in the pictures, or no. Yeah, it's not a unique assignment of significance to this. Anyway, so a matrix can have it has two legs. It has, in principle, two different dimensions, D1 and D2. Special case is the identity matrix. And the identity matrix we represent with just a line. And this means the delta. So the components of the matrix are just deltas of both indices. And a generalization of this is like the copy tensor, where we can put some indices, and this would be this kind of identity embedded in a larger space that we were seeing before, only that my legs are all pointing wherever, and I'm not saying that this is really like a vector, so all of them are vectors or not.
This is like the identity.
Sorry? Yes. That represents that this is a tensor with three legs, and the only components that are different from zero is when the three indices are the same. Exactly. It's a product of delta ij times delta jk. Yeah, those are the only. Well, this is the value of each of the elements. Yes. Sorry, there was another.
I wanted to ask you.
Exactly.
You answered. So this is the tensor IR which appeared in
Exactly. Only that my legs are not. So I'm not making distinctions of whether a leg is so it's a vector, it's an input or output.
But he wasn't.
But it's the same thing. Yes.
He wasn't either.
Exactly. It's the same thing. So yeah, homework could be like putting many of the content of the first talk in this pictorial language, so that I, for instance, could understand it better. Anyway, so no, but I think it's possible. So many of these things can be represented in this language, and it could be done much more rigorous in that sense to embed all this meaning. Only for the algorithms we typically don't need so much, and we are just using the pictures to have a compact language. Okay, so the basic thing that we do with tensors in these algorithms is contracting tensors. And contracting tensors means basically like the simplest thing, we would have two vectors to take a scalar product of two vectors. So a contraction in general is something like this, where we have two tensors and we join them with a leg, and this just means to take the product and the sum over this common index of both tensors. So in this case, it's like the simplest case, a vector, scalar vector, a scalar product of vectors. But of course, we can go further and take a matrix times a vector, or a product of two matrices, and so on, right? So, okay, that's a way to put it, if you want. You could just define, or say, you have two vectors, and then you multiply with a delta, which is a, yeah, in this case, it would be a matrix. Sorry?
Look at unitary invariant.
I'm not sure. So I'm just saying here that this is an operation. So I'm not saying what properties of symmetry have these tensors at this moment. So there might be properties of symmetry. I'll talk about asymmetry that is in this kind of construction later. But right now, I'm just defining the language. So I'm just saying, you have a tensor with all its components, whatever it is, and a contraction is just joining one of these legs with another tensor, and this just means taking the product like you would do with matrix product. Okay? No, but then I would, okay, in this language, I would put a matrix inside. I would draw another matrix inside. So a leg here is just a delta in this language. Okay. Right. So these examples are just like the simplest ones. And if you see what comes out of this, well, you can see the whole thing is a tensor, right? Because you see how many open indices you have. Like for instance, in a matrix times matrix multiplication, you have a resulting object that has two open indices. So it's a tensor with two indices. It's again a matrix, but it has some structure, which is this matrix product structure. And well, in algorithms, it's very important to keep track of how much computational cost these operations have. And it's easy to compute the computational cost of these operations because, okay, if you want to take a scalar product, you have to take so how many elementary operations you need to do? You need to take the product of each component of the pair of vectors and then sum them all. So this is like the operations and so on. So for a matrix times vector, you have to do this d1 times for like all the components of the resulting vector. So this is like the product of dimensions, the cost of the product of dimensions. And for a matrix is again the product of all the dimensions that appear here. And in general, that's true that if you have a contraction of two tensors with different legs that are contracted and different legs that are open, the cost of the operation will be the product of all indices that appear, whether they are open or closed. And this is important for the algorithms because we want to have efficient algorithms, of course, to manipulate these things. So some, say, basic ingredients in our tensor network algorithms, or one of the most important routines that we use is the singular value decomposition. And well, the singular value decomposition for a matrix is actually like the lowest rank decomposition of the matrix. And graphically, in our pictures, what we write is that, okay, given any matrix with, in principle, a rectangular matrix, so an arbitrary one, two different dimensions, it can be always written as a product of, say, two unitaries times, in between a diagonal, right, of positive, so non-negative elements. And because these matrices are actually like isometries, because the dimensions do not need to be the same, so we can keep track of this property in the language by drawing triangles for the isometries. It's the only case where we use a particular shape to capture some property of the tensor in the diagrams. It's not always made explicit in the pictures, but sometimes it is, and it usually means that. So an isometry is one of these triangular tensors in our language, and it has a property that contracting on the larger dimension, you get the identity. And well, contracting in the smaller dimension, what you get is a projector because you don't have enough rank for the whole identity. So this is just a sort of ad hoc notation here, just to mention to make it clear that it is a projector. What is used generally is the triangular shape for the isometry. And well, the cost of the singular value decomposition is also very important in the algorithms. It goes like the product of like the largest dimension times the square of the smaller dimension. So, okay, what other things can we see in this picture? Well, if you have a matrix, you can just have this kind of diagram. And if you think what this diagram means, this is, you see a product of the matrix with some other matrix, which is actually the identity matrix that I showed before. So we are contracting both indices. I think this is not working anyway. So we are contracting both indices of the matrix with both indices of the identity matrix. So what we are doing there, and then summing, of course, because I told you that the contraction is a sum too. So what we are doing there is summing the diagonal elements of the matrix. So what we are doing there is the trace of the matrix. So this diagram means the trace of the matrix. And you can do it for higher dimensional objects. And you can take a trace over one of the indices. And this is what we call a partial trace of some of these tensors. So this is the end of the pictorial representation. And it's a very compact way of introducing the language. But you will see that it really is useful to tell you about the properties of tensor network and their algorithm. Okay, so back to, yes?
Ask a question about
yes.
At some point you said that this contraction, if the tensor network, the way you contract it is always the product.
For two tensors.
For two tensors, okay.
Yes, yes. No, if you have more tensors, then it's really much, of course, it depends on the order of contraction in a non-trivial way. So it's a hard question, a hard problem to figure out what is the best order of contraction. But just for two, so if you have an algorithm that specifies a way to go through your tensors and perform some contractions, then you can compute the cost taking into account this lowest level ingredient. That's, yeah, thank you. Okay, so back to the quantum many-body problem. What we want to do is to express states of a quantum many-body system. So a quantum many-body system, we can always write in a tensor product basis. So if we have these n individual components of our system, and each of them has a Hilbert space of dimension small d, Then we can take a basis of each of them and construct the tensor product basis and write our arbitrary state of the global system as a linear combination of elements of the basis. So this would be this equation that appears here. And of course, we can think of these coefficients as tensors in this n-leg tensors in this d to the n dimensional space. So this is, of course, an exponentially large space, and it's an exponentially costly problem if we want to describe these things exactly, which means that if we want to do things numerically exactly, we can only do small systems. And this is not what people want to do in, say, quantum many-body physics. You want to extract properties of very large systems that appear like as collective properties when you have many components. So this is a limitation if you want to do things exactly. Yes, so yeah, small d could be, imagine that they are qubits. Small d could be 2 in most of the examples that I'm going to show. And n is how big the whole system is, how many of these you have. So as you make n larger, then it's exponentially large, yes. Okay, so what is the idea of tensor networks? Well, the idea of tensor networks is to think of some states where you don't have this exponentially large number of possibilities. You restrict your possibilities to subsets of the Hilbert space where the coefficients have some structure. And that structure is precisely a tensor network. So this picture here is a completely arbitrary one. So this would be a tensor network, but this doesn't have a name. It's just a cartoon picture, whatever tensor network that is. The idea is that you will have a polynomial number of smaller tensors contracted in some pattern, and then you can parameterize this efficiently because it's a polynomial number of tensors, and this somehow allows you to work with this numerically for larger systems. The number of legs is fixed. Yeah, exactly. So now you could take this object here and contract everything together, and then you would recover something like this. You will have all the coefficients. Well, you could do that, but the kind of families we have won't be like that. We will have a lot of tensors. So at the end, you have a lot of legs, but not in the same tensor. So each tensor will still have few legs if you want, but you will have many of them. So this is just the general idea. And yeah, okay, another way of thinking about these objects, and that's precisely going in that direction, of these objects in this quantum many-body context, is that you have this kind of local pieces that are like Lego blocks. And with these small blocks, you can construct larger and larger states that give you like global properties, collective properties. So an example in the context again of quantum many-body physics, which is very natural, is to think of mean field approximation. And in mean field approximation, what you have is really just product states. And product states are used very often to figure out properties, physical properties of given problems. And this is so because we can compute with them efficiently. And although it is a like very, very rough approximation because we don't have any correlations, it's like a product state, we know that it still can give us at least some qualitative answers about the physics of a problem. So it's very useful. So the idea is that with these tensor networks, sorry. Yes, so mean field approximation is the name they give to it in, say, condensed matter or so on, but it's really like thinking of product states. Like you discard correlations. So for instance, you restrict the set of states. Imagine that you are doing a variational algorithm. You could just search over the set of states which are a product. That would be a mean field approximation in our tensor network language, if you want. It, of course, simplifies a lot the calculation and allows you to solve problems in this limit. Yes?
I think mean field approximation, you think of them all the same, product of the same, or a product of different?
It depends. Like, I would say that in condensed matter, often it's always the same, but I would include any product state with different tensors in the same bag. Sorry? Yes, exactly. Yeah, thanks. Yeah, right. So that's like the simplest approximation you can do. Still in physics is useful, but of course it doesn't capture everything. It doesn't capture any correlation, so this is not enough for what we want to describe. And the idea is that tensor networks allow you to go one step beyond that. And well, of course, you can ask immediately, okay, but this is such a brutal approximation. Why should this be useful at all? If you are trying to describe this exponentially large Hilbert space, why should this be useful at all to do this kind of cuts? And now suddenly you only have polynomial number of parameters. And the idea is somehow that you don't want to describe the whole Hilbert space. You are interested just in these physically relevant states. And you can focus a lot on these ground states, thermal equilibrium states, and so on, because they give you the properties of matter. So the ingredient here is that a random state in the Hilbert space is very difficult to describe because you would need these exponentially many coefficients. But what you want is very far from that. So what you want is just say, if you think of product states, these are a very small part of the whole Hilbert space. And this is, as I said before, not enough. This would be what mean field theory is describing. But what we want to describe is states that appear naturally. And these states that appear naturally are just something more than product states, but very far from all the states in the Hilbert space. And what people say about this, usually in the literature or when they give talks and so on, is that we want to describe the interesting or the particular corner of the Hilbert space, meaning that these physically relevant states are just very special. They are not like all states in the Hilbert space. And okay, tensor networks do not need to worry about all the Hilbert space, but just about these physically relevant ones. So the goal is precisely to find this state, or give some good descriptions to them, good approximations to them. So what we want from the point of view of these things being useful is, well, on the one hand, that we have an efficient representation, which I already sort of argued about with the number of tensors. You can get an efficient representation, but that's not enough if you want to, say, predict properties of your systems. You want to also be able to compute observables, so compute expectation values in these states. Once you have this description, you want to know what will be the physical properties of this state, and then eventually compare it to experiment to see if it is a good description or not. And ideally, you also want to have algorithms to find what is the best description within this set of states, say like a variational algorithm that gives you the best guess for one of these equilibrium states in terms of this description. So this is sort of the wish list for any of these tensor network algorithms. I still didn't tell you in a very concrete manner what is the main ingredient for these tensor networks to work, right? So it's still a very rough approximation. So the question is, what are the physical properties that make these tensor networks interesting, that makes it useful to work with this tensor network? And it turns out that the answer comes precisely from quantum information, because the interesting property that tells you that you can describe these states much better than like the general states in the Hilbert space is the entanglement structure, that they have some particular entanglement structure. So if we have a, say, system like this I don't know, shape is just meant to be a system, and we consider a bipartition in two parts, A and B. Like we can have a product state, which would be like we take a vector state in A, a vector state in B, and we have a tensor product. But we can also have entangled states where we cannot write in that way as a rank 1 tensor at all. So this is true for pure states at least. So and the measure, so states like that we cannot write in that way, we say they are entangled. And the measure to know how much entangled they are is entropy of entanglement. And the entropy of entanglement we can compute by computing the reduced density matrix, like tracing out one part of the system, so getting the state of the other part, which is the reduced density matrix, a mixed state, and then computing the von Neumann entropy of that operator. So vectors, so states are normalized vectors of the Hilbert space. Yes, pure states are normalized vectors. Yes. Okay. So what is the entanglement in these states that we want to describe? Well, the thing is that they have very little entanglement. So random states in the Hilbert space have a lot of entanglement, but these states have very little compared to that. And well, this is sort of the key idea, that the states that we want to describe, so this understanding that these states that we want to describe have very little entanglement is what really makes it possible to describe it as tensor networks, because tensor networks, in the end, are, say, also states with little entanglement, or that parameterize particular entanglement structure. So a way to make this more concrete is like how much entanglement we have in these equilibrium states or ground states, is the area law of entanglement. So if we consider, now I'm picturing here a system which would be on a square lattice, so each of these circles would be one of the systems, so one of the individual quantum systems which have like one of the qubits in my system, and they sit on a square lattice. And we consider a certain state and a bipartition of my system in two parts, A and B. Now for a random state of the Hilbert space, if I do that, so I take one random state of this very large system, and look at how much entanglement I have between A and B, this grows as the number of qubits that I'm catching inside A. Okay, it's like, this is called a volume law, because if you would make this in a three-dimensional picture, it would be really like the volume of A. So here is a two-dimensional picture, but we call it the volume anyway. So for finite range Hamiltonians, the intuition is that, well, the correlations in your ground state correspond to the interactions in your Hamiltonian. And they are short range, they decay, right? So you make the system very large and the subsystem A very large, somehow the particles in B, the qubits in B, do not know about how many particles you have inside of A. And the other way around, they are too far away. The correlations do not reach that far, right? And then the amount of entanglement you can build up goes like the size of the boundary between both regions, because it's some particles around the boundary that will contribute to that, but not all of them. This is, of course, just a hand-waving explanation of what is going on here. This is the intuitive picture. But this is really what the area law tells us, that the entropy between these two parts grows like the size of the boundary. And yes, yes. Of course, then it might be that you might run into problems if you want to do this computationally with the algorithms. But yes, for the area law, that's true. So, okay. So what I said was just the intuition and what you expect from short-range correlations. Rigorously, it's only been proven for the one-dimensional case, so when systems lie on a line, and for local gapped Hamiltonians. This was rigorously proven by Matt Hastings in 2007. And that ground states of these Hamiltonians satisfy exactly this area law of entanglement. If they are not gapped, so if the Hamiltonian is not gapped, there is not a gap of energy between the ground state and the first excited state, it closes. This is what happens for critical systems. Then the theorem is not true anymore because we don't have all the conditions. But it turns out that this case is also known, what happens in one dimension. And there are corrections to the area law. There is more entanglement than the area law, but it's only small corrections because they are only logarithmic. Yes, local means that your Hamiltonian is a sum of terms which only have short range. They could be a few, so they could act on a few sides, but the range of the terms does not grow with the system size. And gapped means that your ground state, so there's a finite energy difference between a difference in the eigenvalue of the Hamiltonian between the ground state, the lowest energy state, and the next one, the first excited state. You can always, it's the smallest, but you can always shift it for this matter, it doesn't, so for this question, it doesn't matter. Yeah, exactly.
What is max?
The largest entropy that you can have. The maximum, because, I mean, it doesn't need to, this is like a scaling statement. So it doesn't mean that it's like that for every cut. You could have a cut where it is smaller than that, for instance. Yeah.
Do you get the half?
Sorry?
Do you get the half?
You get typically the central charge of a conformal theory and things like that. But I don't know if this answers your question. So my statement is just about how it grows when you make the system larger, right? But yes, you're totally right. For critical systems, you have a universal coefficient in front, because actually this result comes from conformal field theory. And then it's so about your question, what I mean is that for a given size of the subsystem A, it's upper bounded by, so the maximum entropy you have between the subsystem A and the subsystem B is upper bounded by something that grows with a subsystem A, but it's not fixed that for every cut you will have the same quantity, right? Both, yeah. I mean, if you have a Hamiltonian which is one-dimensional, then somehow you can draw your system in one dimension, right? You can always write your system in, I'll show you in a second. You can always write your system in one dimension and consider a Hamiltonian that is not local. And then it might be local if you write it in 2 dimensions, or the other way around. Probably I said it the other way around to make it more confusing. But yeah, I guess you get it. Okay. Right. Okay, this is, so you see the picture is really clear for one-dimensional problems. For higher dimensional problems, for 2 dimensions, for instance, there is not such a strong result. What there is like an observation that area law is true in many, many cases, in most interesting cases, even in some critical cases. And in some cases, it's been found that it is violated, but again, with small corrections that are logarithmic. But there is not such a mathematical proof. And what is known true is that in arbitrary dimensions, there is an area law for finite temperature state. But then you have mixed states, and the quantity is not the entanglement entropy, it's mutual information. But also, yeah, they have small correlations. Yes? Exactly. So the area law in one dimension means that the entropy is upper bounded by a constant. Yes. Okay, so this is sort of the guiding light about looking for good ansatz for ground states or thermal equilibrium states of like this local Hamiltonian. And this is somehow what tensor networks try to do in a very general way. So in particular, there are some families that are like the most popular ones that fulfill this area law by construction. So you really construct families of states which have a tensor network structure, and they fulfill the area law by construction. And these are matrix product states in one dimension and PEPs in higher dimension. And there is a picture here of the tensor networks that they represent, but I will show in a second more properties about them. They are not the only ones, and then you can think of tensor networks or tensor network states as, in general, as an ansatz for quantum many-body states, which is based on entanglement, or in which kind of pattern of entanglement you want to reproduce. And as I said, there are other tensor networks that do not fulfill the area law, and this would be trees, for instance, or Mera. I hope I have some time today to show you a little bit more about them. But I will spend most of the time talking about the properties of the one-dimensional ansatz, which is the matrix product state, and the generalization, which is PEPs. Are there any more questions now?
You have a morning.
Okay.
So I think what is important in the connection right geometry networks in networks and MPS, the entire GL axis.
Mm-hmm.
So there is actually what comes out, like if you vary over all of them, I'll try to write, or I mean, if you take closure, you get that connection. But if you look at this mirror part, there is some unitary constraints in the object. It will actually prohibit the appearance like a dry structure that say you would like to study. That is why you have them in view.
Sorry? Yes. I'll probably say a bit more about the construction later, but thank you. Okay, so let me talk about like the matrix product states. Matrix product states are really like the paradigmatic tensor network family, because on the one hand is the one that we understand the best mathematically, but also it supports the most efficient algorithms. And then it's really like given rise to like a change in the way of doing computational condensed matter physics. So a bit of the history of this field in the context of quantum many-body problems is like sort of this view, which is, I said, partial to this topic. Like the first MPS appearing was the AKLT model that was proposed in 1987, as a state that is actually the exact ground state for one of these local Hamiltonians in a spin chain. And the way it works is the following. So you have a chain of quantum systems with spin 1, total spin 1, so the physical spin 1. And the model is constructed in the following way. You say, okay, spin 1, I can, this is angular momentum, I can construct it from two, say, virtual particles of spin 1/2, like summing them and projecting onto the symmetric subspace. So the way you construct a state and a Hamiltonian is by considering that these virtual particles of spin 1/2 are maximally entangled, are in a singlet state, total spin 0, with their neighbors, and then you project locally onto the symmetric subspace to have the physical degrees of freedom, which is spin 1. And because, I don't know if I have the picture in here, because, say, if you consider two sides, you have 4 of these virtual particles. The 2 in the middle are in a total spin 0. They are in a singlet state. They are maximally entangled, total spin 0. And then you are adding 2 more spin 1/2 particles. The total spin that you can get is never 2, because you are adding 0 plus 2 1/2. Okay? So if you now project these two particles, these two sides, onto total spin 2, you will get a 0. So this state vanishes exactly under this projection. So you can construct a sum of projectors for each pair of sides, and this you call a Hamiltonian. And that's actually the model. And then, of course, you have an exact ground state for this Hamiltonian that you have constructed. And this is like really the first MPS appearing in this literature. So afterwards, this construction was generalized by Fans, Nachter-Gele, and Verna in these finally correlated states. And independently from that, there was the development of the DMRG algorithm by Steve White, which was a numerical algorithm to solve quantum many-body chains, and so strongly correlated spin chains. And it turns out that this is a very accurate algorithm. It gives very good results. And since then, it's really like the state-of-the-art way of solving strongly correlated quantum systems in small dimension. Has been applied to quantum chemistry, 2D, and so on. But at the moment, it was like not directly connected to this construction. So it was soon afterwards that people realized that it was actually sort of the same thing, that DMRG was actually looking for the best solution among this set of matrix product states. And at the beginning of the 2000s, then came the tensor network language with the quantum information understanding of these entanglement properties that sort of characterize this construction. And since then, this gave, so opened the possibility to generalize this very successful DMRG algorithm to many other cases, including going to higher dimensions. So this is the sort of context in which tensor network states are now regarding this quantum many-body physics or condensed matter community. So, okay, what are these matrix product states in the sense of the pictures that I was showing before? So I was saying that the general state of a quantum many-body system is this kind of box with n legs, and this is the general expression of the state. So it's a ket, it's a vector of the Hilbert space, which is just a linear combination of states of the bases, and these coefficients are really this tensor with n legs. So the idea of matrix product states is that these coefficients are restricted to ones where the structure is that of a chain of tensors like this. This is, of course, also this has appeared in other contexts, like in say in applied mathematics, and they call this a tensor train because of obvious reasons, because you have one tensor after the other, right? So in physics, it's called a matrix product state because if you write explicitly the coefficients in the bases, what you get is precisely a product of matrices, because for a given element of the basis, you fix this index, so the open index, which corresponds to the physical one, and then what you have is like one index is collapsed because it's fixed to one value, so what you have is a matrix, and then you have a product of matrices. And the trace appears because you can do this for a periodic system where the first and the last are connected. But you can also do it for an open system where they are not.
I1 is not a power.
Sorry?
I is not power.
No, the I's are the, yeah, maybe I should, yeah, I should put them in brackets or something, sorry. Yeah, they are the indices. They are summed actually over the different indices of the bases.
Trace.
Yes, this is like the middle of the state. So yeah, I should put like dots there because it could also be open. And then what would happen is that the first and the last are just a vector, not a matrix. They don't have an open index. Okay, so the number of parameters that you have in the ansatz, of course, grows linearly with the number of sites. And then, because for each site you have one tensor with one open index, which is the physical dimension. This is fixed by your problem. But then you have some freedom in how big these tensors are. And this extra dimension that you put in there, which is the virtual dimension that connects one site to the next or one tensor to the next, is called the bond dimension. So the number of parameters grows linearly with the system size and linearly with the physical dimension and with the square of the bond dimension. So then you have something which is efficient in the system size as a descriptor. Also, it fulfills the area law by construction. This means that there is an upper bounded entanglement. The entanglement is upper bounded by a constant. And I think I have a picture. Okay, I think I have a picture of the area law in a second. But let me first show an example, which is like the simplest example. So what kind of state you get from that construction. So I think this is one of the simplest pictures that you can get. And it's the following. So you say we have qubit. So the physical dimension is 2. We have two states, like the small i's can take values 0 and 1. And so you have, we construct an MPS with matrices of size 2 for each of these physical components, 0 and 1. And these matrices are the ones that I'm showing you in here. And if you just expand this expression, taking all these matrices the same, I'm not writing the boundaries, so just take the center of the chain and see what comes out. So what you will see is that when you take products of these matrices, of course, some products vanish. If you take 2 consecutive A1s, it will vanish. But also, because A0 is just the identity, if you take 2 A1s anywhere, it will vanish. So what you get from here is that the sum is a sum of states that have exactly a 1 in one of the sites and 0 everywhere else. So it's a W state that appear also. Sorry? Yeah, well, I'm saying I'm cheating a little bit here because I'm not talking about the boundaries. So I could put boundaries. I don't know. I think it's not in this picture, but I could just make it so put some tensor at the beginning and at the end, because as I said, if I put open boundaries in my MPS, I don't have a matrix at the beginning and at the end. So the first and the last are just vectors. So I can just select a vector, so row vector at the beginning and column vector at the end. That so prevented all zeros, and that's it. So I'm just not writing it just to see the kind of linear combination that you have in here. Yeah. This could be there. If I just put the trace, it would be there. What I'm saying is that I'm cheating a little bit because I can remove that by just considering an open boundary state where my first tensor is different and my last tensor is different because they are vectors. They are not matrices anymore. Or, well.
I could imagine that if you just added zeros there.
Sorry?
In terms of.
So you want the zero, okay. So yeah. No, like it's written in there, the zeros are included. So I'm just saying you could just, to make it the W state, you should remove it by putting some boundaries to the tensor. Yeah, you can do it. Yeah, you can do it. You can do it. I just chose the simplest case where all the A's are the same. But of course, the A's can be different side by side. And then they can have different weight. And of course, you can have more complicated things. This is just to see what comes out if you put some simple matrices in there with what kind of states you are describing. Yes. Okay, yeah, the picture about the area law. I said that this has the area law by construction, and this is very easy to see. So I'll just like to show it with a couple of pictures. So as I said, this is a generalization of the AKLT construction that I was describing before. So what you can do for MPS, it's a completely equivalent construction from just defining them as I was doing before. This is states that have this structure in terms of tensors. So you can consider that for each site in your system, which is each of these circles, you have two virtual particles. And these virtual particles, virtual systems, if you want, virtual quantum systems, have a physical dimension, so which is virtual because they are virtual particles, capital D. So for each site, you have two of them. And then we fix a state of these virtual particles, which is maximally entangled with their neighbors. So I have two of these virtual particles per site. I take the, say, left particle on one side, maximally entangled with the right particle on the neighbor, and the right particle maximally entangled with the left one on the neighbor. So this maximally entangled state is just, say, because I'm considering qubits, 0, 0 plus 1, 1. I'm not putting normalization in there. You can put it if you want, or you can just normalize the state afterward. So now, because these are not my physical degrees of freedom, this is not the state I want to describe, I have to somehow map the virtual degrees of freedom onto the physical ones. And this map, I have to specify, right? Here is where the variation of the parameters of my state will be, because what I did so far is fixed. So this is a fixed state. And now what I apply is this kind of map on each of the sides, so that it maps the state of the virtual particles onto the physical degree of freedom. And I have some coefficients. And you see, it's not by chance that I put an A there, because that's precisely the same coefficients that appeared before in the tensors. So if you just do this, you see that you get exactly the same kind of states that I had before. Now, how does this have the area law by construction? Well, it's easy to see, because if we want to see how much entanglement you can have in this kind of construction, we just cut a subsystem of our chain. Okay, now it's a bit of a small subsystem because it's only two sides, but you can imagine there are more sides in between, and you will see that nothing changes. And we want to ask how much entanglement you have in the reduced density matrix. So how much is the entropy of this reduced density matrix of this subsystem? And then there is say, basic property of entanglement, which is it cannot increase by means of local projections, of local operations. And what we are doing there with these maps is a local projection. So the entropy that we have cannot be larger, the entanglement that we have cannot be larger than what we had with these maximally entangled pairs that we put at the beginning, right? So at most is this kind of thing. And now the state that I had with the maximally entangled pairs, it had maximally entangled pairs between my subsystem and the outside just on the boundaries. But inside I just had singlets, so maximally entangled pairs of the virtual particles that do not contribute to the entanglement. So those I can remove. That's why if I had taken a larger subsystem, it would be the same thing. And then, of course, this is a maximally entangled, so I have two maximally entangled pairs that I'm cutting, and they have dimension capital D. So the largest entropy that I can have in there is 2 times the logarithm of the dimension that I put. Yes? Yes, so, okay, you have a system. Okay, this picture is, I have to change this picture. This is not an MPS anymore. But this is my system, right? And I constructed it in the way that I showed before. So now I'm asking how much entanglement I have between a part of my chain and the rest. So I cut my system in two by considering a subsystem in the middle. And this subsystem has size capital L. Then I go back to the way I constructed the state. And then the way I constructed the state is I started with these maximally entangled pairs, and then I did something local. This something local cannot increase entanglement, so I can say upper bound. And then from that moment on, I just need to see how many of these maximally entangled pairs I'm cutting. And because I'm only cutting 2, because it's a one-dimensional system, then I cannot have something that depends on the subsystem side. And then the area law is sort of included in the construction. Okay, that's a very important property, but there are other properties about this matrix product state. So one very interesting property is that any state of like this large system with n constituents can be written as a matrix product state. The way to see it is that, okay, any state we can write with this generic tensor that I drew before with the n legs. And what we can do is to apply a singular value decomposition of, say, the first index with respect to the rest. And this will give us something which, because say, number of singular values is upper bounded by the smallest both dimensions of the matrix. Okay, maybe I go one step back. When I'm doing this, in the moment that I'm doing this singular value decomposition, what I mean is that at this moment I reinterpret my tensor as a matrix of like one leg versus the other. Okay?
Just so confused about the state before. That's true for the rank. Really true for the
Sorry, what is true?
So the monotonicity
Mhm.
that you just said that
Yes.
that's true for the
Yes. They cannot increase under local. So it's entanglement entropy between one part of the system and the rest. And it cannot increase under local projectors, which is what I'm doing. So that's the only thing I'm using. Okay, so back to the singular value decomposition. So a bit of the clarification of what I'm doing in here is that I'm picturing my state as all these coefficients, but when I take a singular value decomposition, what I do is I reshape it as a matrix, rearranging the indices in the way that I find most convenient. And in this case, I'm just rearranging the first index in here versus the rest, and I'm applying a singular value decomposition. So how many singular values I can have? Well, the rank of whatever this is, I don't know, because this is a generic state, but it cannot be larger than the smallest dimension in here, which is, of course, if this is a large system, will be the first one, small d. And I can continue. Now I can do the same thing for the big tensor that I have in here, doing another singular value decomposition. Now I can have, in principle, d squared if all the dimensions are the same. And I can continue, do the same thing, but of course, all the time, the bound will be with the smallest of the dimensions that I have on both sides. So the largest dimension that I can get if I go doing this is like what I have in the middle, if you want, when I have like d, small d to the n halves. So I can do this exactly without throwing anything away, just an exact description of the state, with bond dimension, which would be these dimensions in between, up to small d to the n halves. Of course, if I have to do this, then I'm not gaining anything by using this description, because I'm again exponentially costly in the system size. But of course, we are interested in cases where this won't happen. However, it is important to know that this is the case, because it tells us that we can use this description for any state we want, and we just might need to increase the bond dimension to capture whatever it is. Okay, this is what I just said. There, yes?
So is there any nice bound on the rank MPS depending on this bond dimension?
Depending on the bond dimension? Yes, okay, yes. I will show it in a second. If you reduce your MPS to the canonical form, then you will explicitly see the rank in the bond dimension. I'll show the canonical form in a second. Okay, so this is just the same thing I said before about this hierarchy of MPSs that go up to covering the whole Hilbert space. The way it works is, of course, that if you have a tensor of bond dimension 1, this would be the case of product states, you can embed it in a larger tensor by padding with zeros, and then you are in a MPS. I mean, formally you have an MPS with bond dimension 2 and so on. So these families include, so with larger bond dimension, include the smaller ones until they cover the whole Hilbert space. So another interesting property is that you have what we call a gauge freedom. And what happens in here is that in these products of tensors, you can, of course, insert any matrix and its inverse, right? And the whole result won't change. So in particular, in matrix product states, you can do that in any of these virtual legs. Now, you could reabsorb, say, one of the matrices in one tensor, one of the matrices in the other, and your tensors change a lot. They look completely different, but the state hasn't changed at all. So this is what we call gauge freedom. Now, this makes it difficult to say things about the properties of the state just looking at the tensor. But luckily, for matrix product states, there exists a canonical form that allows you to really characterize states by one form of the tensors and then compare states to each other. So the canonical form can be found by asking or imposing these properties on the tensors. Let me just explain what this means. So I'm showing both the expression, and so you see now, yeah, that's why I'm not using brackets for the indices, because often when we have not translational invariant states, we use brackets to indicate the site and then the index goes without a bracket, but it's never an exponent, so it's still indices. Anyway, let me go to the picture, because I think this is why the pictures are good, because we can explain what the properties are. So what this picture means is that you take a tensor of the MPS, contract with its adjoint. Here is where you can enrich the diagrammatic representation by using some special symbol to indicate the complex conjugate.
Okay.
This one is the identity matrix, yes. Yeah. Since I said that where the legs point doesn't really matter,
Yeah.
in here is just to keep the same shape of the thing on the left. So what you get is that if you contract two of the indices together of the MPS tensor, the tensor has 3 legs, you contract the physical and one of the virtual ones, you obtain the identity. And this is contracting on one side. What you can still get is that when you do a similar thing on the other side, you cannot get exactly the same property, but you can get it up to a diagonal. So you can find a diagonal matrix such that when you contract with the diagonal matrix, you get another diagonal matrix. If the state is translational invariant, then there is only one of it. But if it is not translational invariant, you can do it side by side. This is a diagonal matrix. So the bracket M means that it can be different side by side. So
you start with a diagonal matrix.
yes, so you take the tensor for the MPS and its conjugate and multiply, say, on the left virtual leg with this diagonal. So probably it's easier to think of the translational invariant case. In the translational invariant case, if you think of this thing without the identity here, right? So this is what we call the transfer operator of the MPS. It's just taking the tensor A and its complex conjugate summed over the physical index. So contracted over the physical index. So this is a map. It's a CP map. So the first property is telling you that the identity is a fixed point for the CP map acting on the right. And the other thing is telling you that there is a diagonal fixed point on the left.
Lambda doesn't have a
No, it's just a matrix. This is really a matrix, 2 legs. Yeah. And it's a diagonal one. Okay, and this matrix is actually, this happens to be what contains the entanglement properties of your MPS. It's really it contains the Schmidt values, so the singular values, if you want, of the cut of your system across that bond when you impose the canonical form. Okay. Well, yes, it's a diagonal positive matrix, so non-negative. No. It's a particular, it's a special one. So it depends on the state. It's not any lambda. That's why I put these super indices here, because it depends on in the general case where the tensors are different from one side to the next, this lambda will also be different from one side to the next. So yeah, it depends on your state. It contains the entanglement properties of your state.
The idea would be that if I decimate enough, I mean,
well, that would be the translational invariant case. So I'm sort of in here being general. I'm not saying whether your state is like a finite one or an infinite one. So this MPS can be defined in a translational invariant manner, so that you are really directly in the infinite size limit, and you just have one tensor. And then there will be also one lambda. But it could also be finite systems with a boundary that are often interesting for practical cases. And then this would depend side by side. In both cases, the thing is true. So this canonical form, well, is unique, and up to like, well, if you have the generacies in these Schmidt values, that you could reorder them, and it can be found locally. Which, I mean, everything that you can do locally with tensor networks is good news, because you can work with the small tensors instead of working with the whole description, which is like exponentially large in general, right? So okay, how do you find this canonical form locally? Well, it's pretty simple. And let me just show you the picture, because then you also see why this pictorial representation is useful. I'll just show the first one, the first part of the canonical form. So you take one tensor of the chain and say, how do I find the canonical form that fulfills this property? So what you want is that contracting the physical direction, the physical index, and one of the virtual ones, you get the identity, right? So you do a singular value decomposition, reshaping this as a matrix of the virtual index that you are not interested in versus the other. And then, of course, you get something which is an isometry here. Now I think I'm not using the triangles. Okay, I'm just not using them explicitly for some reason. I thought I had changed the picture. But okay, this is an isometry, so it fulfills this property that when you contract on the large dimension, you get the identity. So if you would contract this isometry with the adjoint in that way, you would get the identity. So this is now what you can use as your new tensor. And what do you do with this leftover part? Well, because the whole thing is, you don't want to change the state, well, this thing you have to absorb in the neighboring tensor. And you can move on. And now you sweep over your whole MPS like that, and you have imposed like 1/2 of the canonical form. What freedom do you have? Well, you can still apply unitaries that won't change the property, right? So if you put some unitary, this thing will still be true. So with these unitaries, you can ensure that the contraction on the other side is diagonal. And that's the only thing you need for the other part of the canonical form. But this is sort of the main ingredient actually for the numerics to be efficient. Okay, this is just that you define the new tensor. Okay, what else do we know about this matrix product states, which is very good for the practical purposes, is that they have this property that I was saying before, that you can extract, predict observables from there. You can compute expectation values. And well, computing expectation values is not for granted, even if you have this kind of description, because if your observable, the thing you want to compute the expectation value of, is a global one, is something that has no local structure, then it doesn't really help a lot that your states have this local structure. You still have exponentially many components of this observable that you need to compute, right? So the way to compute an expectation value usually would be to sum over like all the coefficients with the corresponding expectation values of the matrix elements of the observable, and well, you do the sum which is exponentially large. So what you can do with matrix product states is for observables which are local or have some local structure. The simplest case is an observable which is just acting on one side. So it's like a one-side operation. Then what you can do is, of course, you could still write the whole expression as before, which is an exponentially large sum of terms in there with all the coefficients. But if your state has an MPS structure, there is a more efficient way to do it. And it is to do first the local contractions of the matrix product state tensors, and then do the contraction along the chain. And why this works is easy to see, because, well, in this case, this is precisely the transfer operator I was mentioning before. This is an object, which if you put it together, that would be the expression. It's a d squared times d squared matrix. And in the case of the operator, well, it's still the same size. It's just a different object with the operator inside. But this is just d squared times d squared. There is no n in there, right? So now, if you just do these contractions first, what you are left with is a product of, well, in the case of open boundaries, where the first and the last are vectors, do not have a bond dimension going out, you will have a product of, say, a vector times a matrix, and each of them is d squared. So each of the dimensions is d squared. So you can just compute this with cost d to the 4. And then you have again a vector, which is dimension d squared. And you can move on and do this along the chain, and you will do it n times, right? But nothing that grows exponentially with n. Actually, you can do it a bit better if you use the structure of the tensors, but that's enough. It doesn't grow exponentially with n, so it's efficient. You can use this also to compute other observables, in particular two-point correlators. And two-point correlations are very interesting things in quantum many-body physics because they behave very differently if you are in critical systems or not. And it turns out that you can compute them in matrix product states because they have the same structure, but they have a very particular property in matrix product states. They decay always exponentially. And the way to see it is precisely with the same pictures that I did before. So now we want to compute what is called a connected correlation function, where basically you want the expectation value of a product of two local operators that act at a certain distance, and you are asking about how this depends on the distance, how far you put them away from each other. And the connected part means that you subtract what is called the disconnected part, which would be just the product of the expectation value of one times the expectation value of the other. Okay, so this is the interesting object in this context. So to compute that, so each of these individual ones is exactly the same kind of expression that I was showing before. But now let's consider a translational invariant case. So really this is very large. Again, we reduce this to the product of these local objects that either contain the operator or not. If they do not contain the operator, then it is this transfer operator that is repeated in here. So depending on the distance that we put in between our operators, we will have more or less products, or more or less factors of this transfer operator. So this transfer operator is not an Hermitian matrix, but in the generic case, it has some spectral decomposition. You will have some generalized one with right and left eigenvectors. So we can use this and ordering the eigenvectors from the largest to the smallest to write explicitly the dependency of this expression on these eigenvalues. And then what you can see is that so we have a first term with the largest eigenvalue, which will be to the power of whatever distance. I've written here x minus 1. It depends on how you define this correlator. It doesn't really matter. And then the next term will be something given by so the ratio of the next eigenvalue to the first to the power of the distance, and so on. So the other values will be smaller and smaller and becoming smaller, exponentially smaller with when the distance increases. And now the only thing that one has to look at, look in here to see what it is like this first factor, lambda 1 to the x minus 1, this is just a normalization factor. So if we just divide this by the norm of the state, this will disappear. And then this first term that dominates the sum is really the same thing as this disconnected component. Because you see, if we would just remove one of the operators, for instance in here, what we would have in the translational invariant limit is like this is an infinite number of repetitions of this thing. In the generic case, this is not degenerate, so you will only get pick up a contribution from the largest eigenvalue. And this will be precisely this one with the R1. And on the other side, you will have the same thing with the L1. So this is basically the same thing as the product of the expectation values. So immediately you get that the contribution, so the first contribution to the connected correlator that I was showing before is given by this ratio of the second to first eigenvalue to the power of the distance. So it decays exponentially. There are more properties that we know about these things. For instance, that they can be prepared efficiently. I'm not stopping at this, but this is an interesting property from the point of view of how realistic or useful this family can be. We also know that they can approximate ground states efficiently. And basically, this is like the key reason why they are so useful in the context of quantum many-body problems. I'm just, I think, jumping a bit ahead because otherwise I won't have time to show all the cases I wanted to show. Maybe this is interesting anyway because since any state we can approximate, so any state we can write exactly as an MPS with a large enough bond dimension. But if you want an approximation, what you can do is to truncate the bond dimension. Every time you do a singular value decomposition, you can throw away the smaller singular values. And if you do that, well, you can upper bound the error that you make in this approximation, and this error is upper bounded in this way that is shown in here by, well, there is a term for each cut that you do in each of the links, of course, and this is really given by how many of these singular values, of these Schmidt values, you are throwing away. And, well, then the conclusion is that you have a good approximation as an MPS if your singular values, if your Schmidt values decay fast enough. And that's basically the property of ground states of local Hamiltonians that allow you to use this as a tool. Sorry? M alpha is because alpha is labeling in this case the cut. So you have a sum for each cut, you have an error. And the M alpha is like, what is the cut? No, what is the largest? Sorry. M alpha is the exact one, the exact value that you would have without throwing anything away. If you do a singular value. No, this is just an upper bound in general. What I'm saying is that in case that this decays fast enough, that these values are small enough that you can upper bound them, then you will know that your approximation is good. And this is what happens precisely for the interesting state. No, the first statement is just general. Of course, it could be very bad if your state is very general. Okay, yeah, it works for pretty boundary conditions. I already said that before. And well, this is a generalization of the AKLT construction, but somehow I'm just jumping ahead because otherwise I don't have time to go over the things. It's only 15 minutes left, so okay. Yeah, they have many properties. We understand many of these properties well, and many of them are interesting from the point of view of being able to use them to describe physical situations. Like, for instance, this thing with symmetries. You can work with tensors that transform in particular ways under some symmetry groups, because this is interesting to describe the physics of the problem that you are looking at. And this is, again, well, very useful. It's very useful not only for the numerics, it's useful also because the structure of the tensors in terms of symmetries tells you which kind of states you can construct when you put all these tensors together. And this is very much connected, I think, with something of what Norbert will talk about this afternoon. So this picture is for one dimension, but this statement is actually true also for PEPs. So this is just some of the properties that I mentioned before. I think I'm jumping ahead about I'm going very slow. So I think I'm jumping ahead to show you the PEPs. I don't know if I can. Yeah, it's not so easy because I just have to go ahead. Sorry about this, because I don't have access to all the slides. So if I have time, I'll go back and tell you about this. Sorry, this is better if I do it in my computer. Oh, sorry. Yeah, I would have jumped over this. Anyway, I think now it's coming. 8 or 18. Sorry, I mean I don't have the. Yeah, tomorrow I'll try to have the double screen, because it's easier. Yeah, sorry. Okay, PEPs. Because I promised that I would say what PEPs are, and so I'm honoring that. So what I just jumped over was the fact that this MPS, I was talking about pure states all the time, basically, with these Schmidt values and so on. But this is really just a description of some vectors in a tensor product structure vector space. And this works also for operators. So one can do the same thing for operators. And these operators could be many-body operators, like a Hamiltonian and so on, or could be states, or could be mixed states. So we can also use the same ansatz to describe mixed states. And then one has to think a little bit about the properties that mixed states need to have, like they have to be positive. And that's not so easy. And there are some ways to still work in the tensor network framework with that. But okay, just a super short summary of what I skipped. So I also wanted to show some of the other families. Matrix product space, as I said, is the one that we understand the best and the one that is most powerful right now for the numerics. But it's not the only one. And also from the numerical point of view, PEPs are very important now, and they are really getting a lot of interesting results and very competitive ones. So let me just show what PEPs are. And it's very easy to say what a PEPs is after presenting the MPS, because it's just the natural generalization of it. So from this construction, where for each site in your system, and the system was a chain, you put two virtual particles, you maximally entangle them with the neighbors along the chain, you can go to any network. And for a regular square lattice in 2 dimensions, you could just say for each site, I consider now I don't have only 2 neighbors, I have 4 neighbors. So I put 4 virtual particles, and each of them I maximally entangle with the corresponding particle in one of my neighbors. So I will have, basically, I'll put a maximally entangled pair along each edge of my graph, whatever it is. So I can do this for any graph in any dimension. For the kind of problems we look at, typically it's most interesting to look at regular lattices, but the construction can be done the same. Okay, so you do that, and then you have 4 virtual particles per side, each of them with dimension capital D, the bond dimension, but then you still need to map this to your physical degrees of freedom. And you do this with the same kind of map that we did before, but now this map, of course, has more components because it has to map 4 virtual particles onto the physical one. So now again, this construction has the area law just built in, because if you want to see how much entanglement you can hold between one region and the rest, you do exactly the same argument as before, and the only thing you need to do to upper bound this quantity is to count how many of these maximally entangled pairs you need to cut. And in this case, because you are putting, say, maximally entangled pairs along each edge of the lattice, this is precisely how many sides you have on the boundary between 2 regions. So this is just ansatz, which has the area law construct, so built in. Okay, so yeah, this is the picture of a PEPS, or one picture of a PEPS. This is another picture of a PEPS because it now has like the physical index sticking out of the tensors, and the tensors have 4 legs connecting, well, in the 2-dimensional case, which is the most usual one appearing in the pictures, you have 4 legs connecting to the neighbors. Well, sometimes people draw them like in a 3-dimensional picture, like if you were looking at them from the side. And this would be one example. So now the physical indices are pointing down, and this is my state. So one very different property of PEPs with respect to matrix product states is that contracting them, computing any expectation value, even if it is local, even if it is the norm, just contracting the state with itself, with its adjoint, is not easy at all. It's just the opposite of that. It's very difficult. So how does it work, computing the norm? Well, you take the state, and then its adjoint, which in this case is just, in this picture is just flipping it, and you sum over the physical indices. So you join the physical legs and put them together, and this is the contraction. So you can now flatten this thing and look at it from above, right? And then you have a 2-dimensional network with no open indices. So really the norm is a scalar, right? So this is the thing. And now these legs, I'm drawing explicitly that they have two legs, because this is the result of putting these 2 layers together. Now, what is different from the 1-dimensional case is that you can try to do the same thing as before, do the local contractions before, and then put them together into the total one. And it does, I mean, it works, but it has a cost that is not efficient as before. You can, say, start on a corner and then contract something in, and contract something in, and contract something in, and you will see that any way you try to do it, the cost will grow exponentially with the system size. In this case, the size is L times L with one of the L. And this is a very fundamental property of PEPs. I mean, contracting a general one is a Sharpie complete problem. And it seems to be a no-go. Then you cannot contract, you cannot compute expectation values. But it turns out that you can approximate them. And actually, for interesting states, this approximation works quite well. And this is what algorithms do. So typically, they do some approximation where you go back to some kind of lower dimensional approximation. For instance, you can see this as a matrix product state from one side. So one edge is a matrix product state, and the same thing is, the next thing is an operator with the same structure. So you can approximate the whole thing as a matrix product state, and so on. This is just one way of approximating these contractions. And this is the way practical algorithms work. They also have this kind of character of being a generalization of the AKLT construction, that you can find a Hamiltonian which is local, for which the PEPs is a ground state. But again, I'm not stopping much in here. Yeah, it's a little less than, well, probably 5 minutes left now, because we have to be on time for. Okay, very good. So I don't know if there are any. Including questions, exactly. So, well, okay, I'm just not stopping very much about the properties. So just show you what the construction of the PEPs is. It has some similar properties to the MPS in the sense that it has this local parent Hamiltonian, and it has this area law by construction, but it has also very different ones in the sense that correlations do not decay exponentially. They can hold correlations that decay as a power law. And this property that I just mentioned, that contractions cannot be done efficiently. So this is just a summary of these properties. So, yeah. Are there any questions here? I think I have to stop, no? Anyway.
Oh, yeah, okay. Let's clap and then take
So, no, okay.